Welcome to the 3.5 podcast, which is all about mass and how it relates to the word inertia. And this is the main concept of it. The more mass an object has, the more the inertia the object's going to have, and the more force it's going to take to change its state of motion. And we'll talk about what inertia really means in a few minutes. So the amount of inertia an object has depends on its mass. And this is basically the amount of material present in an object. So we say that mass is the measure of the inertia of an object. Now, if you were to take a small object, or any object, and you were to kick it, you could tell how much mass has by how difficult it is to move the object. So if we kick an empty can, we're going to see that it moves pretty easily. But if we kick a can filled with sand, we're going to find that it doesn't move that much, and that's because there's more matter in that can. So I used to ask my daughter when she was younger, when she used to drink out of one of these little sippy cups, I used to say, it's getting close to bedtime, how much milk do you have left? And what she would do is she would instinctively shake the cup. And what she was doing was seeing how difficult it was to move the cup. And the more difficult it was for her to move the cup, the more milk she had left in her sippy cup, the more matter that was in her sippy cup. And I always thought that was really interesting, that she instinctively knew how to figure out how much milk there was without being able to actually see the milk by shaking the cup. So let's talk about what mass is not. It is not volume. Volume, we know, is a measure of the space an object takes up. And the units we've used a lot here is cubic centimeters. You can also use cubic meters, but we've talked in terms of liters a lot. Mass is measured in kilograms, and mass is not a measure of space. Let's look at this example to illustrate that. We have a feather pillow or a battery, and the question is, which one has more mass? Well, the battery has more mass. It's more difficult to set into motion. It's more difficult to lift up. It's more difficult to stop. So the battery has greater inertia, and therefore it's going to have greater mass as a result of having, as evidenced by the greater inertia. Now, a pillow, though, has a larger size, which means it has larger volume. But we know it has smaller mass. It's very easy to pick up a pillow and toss it. It's very difficult to pick up a battery and toss it. So let's not confuse mass with weight. The amount of matter in an object is often can be figured out by how much by its gravitational attraction to the Earth, and that is what weight is. It's the gravitational attraction to the Earth. But remember, mass is the measure of the amount of material in an object, whereas weight is a measure of the gravitational force acting on the object. And we're going to see why there's a problem using weight to describe how much matter is in an object. Let's say we have our stone, and we have it here on Earth, and we also then look at it again when it's on the moon. The mass of the stone is going to be the same in all of the locations because it has the same amount of matter. There's no change in the number of atoms in that stone. It's going to be the same in all locations. However, the weight will be different because the amount of gravity is different in all those three places. If you want to test that, you can shake the stone, and it's going to be just as difficult to shake in the weightless state out past Earth's orbit, out past Earth, between Earth and in outer space, as it will when it's sitting on Earth itself, where you would experience weight, gravitational pull on the object. So the stone's inertia of mass is a property of the stone and not its location. And you would need to use the same force to shake it on the Earth as you would on on the moon where there's less gravity, or in a force-free region of outer space. So let's define mass and weight as follows. Mass is the quantity of matter in an object, and it's a measure of the inertia of an object, or the laziness that an object exhibits in response to any effort to change its state of motion, such as starting it, stopping it, making it turn. Weight, though, is the force of gravity on an object, and you can see that in outer space, if there is no gravity pull, then the object is not going to have any weight. Now, these are proportional to each other in a given place, meaning that an object that has twice the mass will have twice as much weight as another object. So that what we say is they are proportional to each other, but we have to stress that they are not equal to each other. We often describe the amount of matter of an object by talking about its weight, by its gravitational pull to Earth. So in the United States, we use the unit of the pound, and in most part of the world, they don't talk in terms of the weight of the object. They will talk correctly in its units of mass, or in units of kilograms. So at Earth's surface, we can say that 1 kilogram has a weight of 2.2 pounds, and that's constant pretty much throughout the Earth. You can pretty much convert from kilograms to pounds, or pounds to kilograms, using that ratio of 1 kilogram to 2.2 pounds. The SI unit of force, we know, is the Newton, and that symbol for it is this capital N. So 1 Newton is equal to slightly less than 1/4 of a pound, the Newton being the SI unit of weight. So if you know the mass of something in kilograms, and you want to know its weight in newtons at the Earth's surface, all you have to do is multiply the number of kilograms by 10, and you'll know the weight of the object in newtons. Now, there are only 3 countries in this world that have not officially adopted the International System of Units, and that's the United States and 2 other rather small countries you probably may have never heard about. And this makes it quite difficult for us when we talk to people from other countries. They're always expressing their weights in, their masses in kilogram, where we're still talking about our weights in pounds. Here's just another example of mass and weight. So we said that a bag that weighs 10 newtons, if we take that bag away from the Earth, we're going to find that because the gravity is less, the bag of nails is going to weigh less. In fact, I'll tell you right now that if you take that bag of nails to the moon, it'll weigh 1/6 the weight on Earth. So it'll weigh roughly 1.6 newtons on the moon, where it weighs 10 newtons on the Earth, and that's because the gravitational pull of the moon is 1/6 that of Earth. So this can be a little complicated, but we're going to go through all the different properties here. Does a 2 kilogram bunch of bananas have twice as much inertia as a 1 kilogram loaf of bread? Does it have twice as much mass? Does it have twice as much volume? Twice as much weight when weighed in the same location? And the answer to nearly all of those is yes. The only difference is that the volume might be a lot different, because bananas are much more dense than bread. So therefore, the bananas will actually occupy less space than the 1 kilogram of bread, even though they have twice as much weight, twice as much inertia, twice as much mass. So review, what is the relationship between mass and inertia? The more mass an object has, the greater its inertia, and the more force it takes to change its state of motion.